Hello everyone, I'm here to present our paper, Extend Your Horizon, a device-agnostic surgical tool tracking framework with multi-view optimization for augmented reality. But before we get into the main topic, I would like you to take a bite of this toy setup. Imagine two users are sitting by the table where three objects are placed on. User 1 can see all the objects alright, and therefore his head-mounted display shows the correct overlay of the object. But user 2 is blocked by the laptop, so in such cases, he naturally should not see the overlay of the block object correctly. And we're just curious whether we can leverage the information from user 1 so that user 2 can still see something. With the system I'm going to introduce today, tracking from different sensors can be combined seamlessly without the need of calibrating them beforehand or knowing their transformation explicitly. Hence, in such cases, user 1 can still see the overlay even when direct line of sight is blocked. So our project is motivated by a simple question. When bringing AR to surgical practices, a common problem is sensor coverage. The problem can be therefore broken down into two aspects. Firstly, single device cannot guarantee reliable and consistent tracking, but this is very critical to surgery. Secondly, different devices cannot easily talk to each other due to the driver mismatch, the interface inconsistency, and so on. It often requires dedicated calibration processes before multiple sensors can be integrated. The common solution to the problem is using multiple sensors with overlapped field of view. For example, in this sketch, we have three optical trackers looking at the shared area. But such a setup requires joint calibration, and the sensors need to stay relatively fixed after the calibration is acquired, and of course, such a system is not AR ready. In reality, to track something, we prefer to have some static sensors with high accuracy and high frequency. We would also love to have some low-cost cameras to provide additional coverage for the field of view. And most importantly, we want to have AR headsets to render track results and provide additional intraoperative flexibility. Finally, a system that can mitigate the differences between the sensors in terms of their accuracy, frequency, and consistency, and doesn't assume the static setup or known calibration. Our solution is to provide a unified framework to adapt different sensors. All the packets will be fed into a central hub that leverages TCP communication based on ZMQ. The hub organizes, synchronizes, and transmits the data between backend and the sensor side. Therefore, it provides a good abstraction, such that you can easily port in any type of sensors and use any type of algorithm for the backend. In our system, we have a multi-threaded program which constructs dynamic scene graph based on the poses, and we optimize the poses using pose-graph optimization, and eventually the optimized pose is fed back to AR headset and renders the object in the real time. To explain how we build a dynamic scene graph, we can look at this mock-up orthopedic surgery scene, where we have two tracking devices. The first one is the optical tracker, the second one is Microsoft HoloLens with tracking capabilities. And we have three objects that are being tracked, which are C-arm, the instrument, and the sawbone. We use a two-layer scene graph to categorize all the entities. For the devices that have tracking capabilities, such as optical tracker and headset, we assign them as active nodes, and for all the other things that are being tracked, we call them passive nodes. Most importantly, DSG allows for online modifications. That is, you can freely connect more sensor or include more markers during the tracking as it will not change the graph structure. So, with such a dynamic scene graph abstraction, instead of measuring object pose from sensors in a fixed world frame, DSG allows us to represent sensors and objects as node in a graph. And the benefit of doing that is we never need to calibrate them globally, and the relative transformation can effectively eliminate the dependency of sensor movements, which I will explain in the next slide. The nodes in DSG are connected by edges. The edges are the measured pose of a passive node with respect to an active node. The measurement or the transformation Tij can be defined using the absolute pose of active and passive node with respect to a global frame. We can perfectly write down tracking model for all the edges, and the objective function can be therefore defined as the total residual pose error on the algebra SE3. It can be minimized by adding disturbance and then iterate. Now let's take a deeper look at those two equations. For the tracking model, Omega is a binary flag that indicates the tracking status. If it's 1, it means the passive node is being tracked by the active node. It will be 0 otherwise. Matrix EIJ is the error matrix of the measurement. On the right-hand side of the cost function, lowercase EIJ is the logarithm map of the error matrix, and it can be further expanded into multiplication of expected measurement Tij times Tij hat. By looking at Tij inverse times AI inverse, you can notice that the sensor motion embedded into these matrices have been cancelled out during matrix multiplication. The next part I'm going to talk about is occlusion handling as we proposed in the very beginning. It is a very big issue, but incorporating the dynamic scene graph make it really easy to deal with. For example, in a case like this, you're missing one edge at the top. That means your active node loses track of one of your passive node. In this case, you can look at other edges that are available in the graph, and you can use graph search algorithm like depth first search to find an alternative path, and then you can re-establish the tracking. Here we have a very controlled experimental setup. We have one Microsoft HoloLens, one Intel RealSense, and one NDI Polaris as trackers. A static marker that is attached to a pole, and a moving marker is attached to the end effector of a KUKA robotic arm. We asked the robot to execute the trajectory with a rectangular shape plus 2 line segments. Here are the trajectories that we recorded from 3 sensors individually and our fused results on the right hand side. We overlay their trajectories on top of the robot ground truth trajectory, and the color of the trajectory represents how far it deviates from the ground truth. As we can see, our system has very low absolute pulse error APE compared to the cases when we were only using RealSense or a HoloLens. Although it is not represented here, but NDI Polaris has a very limited FOV, and our system can really expand that even though they're having the similar performance in terms of APE. To further validate our system, we also prepared a mock-up or setting where we have 2 users wearing headsets. We also have an Atraxis Fusion Track and an NDI Polaris, both of which are optical trackers, and we use Atraxis as the ground truth because it provides better tracking accuracy. NDI Polaris and both HoloLens are used to track the reflective markers laid on the operation table. So this is like the number 103 frame from the perspective of the user on the right. At this time, you can see that all 3 markers are being tracked. There is no occlusion, so all the markers come with a little green sphere on top of it, indicating the marker is now visible. And as time goes on, at frame number 115, when the user deliberately cover one of the marker, you can see the green sphere turns into a yellow ellipsoid, and the ellipsoid itself represents how much uncertainty you get on all 3 directions. For the qualitative experiment, we also used a tracked stylus to draw a word of IEEE VR on the board. This figure nicely reflects the features of different sensors. HoloLenses have a good quality of tracking, but it may drift under large or fast movement of the headset itself. You can see what happens to the letter V in a small portion of the last letter E. And if you look at the second figure of NDI, all the tracking seem to be very good, but we're completely missing the letter I here. That is because NDI is known to have a narrow FOV, so it's hard to capture the full length of the entire word. After combining these 2 using our proposed system, you can see that we are effectively ruling out the significant drift created by HoloLens, and also we're compensating for the lost track portion of NDI. Even though there are still some outliers in general, it gives a pretty good tracking results compared to the ground truth collected by Atraxis. To briefly summarize our paper, we propose a system or a framework that is device agnostic and unified for dynamic scene graph. Because of our abstraction, when we calculate the relative pose or the measurement, we don't have to explicitly know the transformation between sensors. In other words, our system is calibration free. We only optimize the poses on or the measurement online as the tracking goes on. And we can handle the occlusion in real time to recover a correct visual rendering. And lastly, our realization can also inform the user about the uncertainty of the tracking at the moment to give the user a better idea of how he can adjust his viewpoint to get a better tracking.